Hi everyone, I'm Abidha VP, PhD scholar at International Institute of Information Technology, Bangalore, India. We are giving a presentation on the paper Coloring a Dominating Set Without Conflict, Q subset square coloring. This is a joint work with our thesis supervisor, Dr. Pradeesha Ashok, and my research colleagues, V Tomar and Dolly Yadav. These are the points that we are going to cover in this presentation. Before introducing a new coloring scheme, the graph coloring is an important problem in the area of graph theory. The vertex coloring is assigning colors to the vertices of a graph with some constraint. Proper coloring is one of such coloring scheme. The origin of this problem is considered as map coloring problem. Graph coloring is not only used in map coloring problem, there are many other real-world applications. Based on different applications, there exist different coloring schemes also. These are a few of the many existing coloring schemes: harmonious coloring, sigma coloring, square coloring, acyclic coloring, etc. Here are some of the many applications of graph coloring problems: frequency allocation problem, chromatic art gallery problem, map coloring, scheduling, pattern matching, timetabling, etc. Let's start with a real-world problem, that is frequency allocation. In this, we have some base station or transmitters, and we have some receivers also. And this transmitter emits a particular frequency, and the receiver connects to a transmitter by a radio signal if the receiver is in the range of that transmitter. Now it is possible that a receiver can come in the range of more than two different transmitters, and if all the transmitters emit the same frequency, then due to frequency interference, the receiver will face difficulty in communication. Now, how can we allocate this frequency in this problem is, we can try with this problem is motivated from one of the coloring scheme called square coloring. In this coloring scheme, if any two vertices are at most 2, then it receives distinct colors. The minimum number of colors used in this coloring scheme is square chromatic number. And this is one of the example, graph G, and the minimum number of colors used in this graph is 5. So that the square chromatic number of this particular graph is 5. Suppose if we color this vertex using a red color, we cannot reuse that red again in this in the open neighborhood of that vertex and the vertices which are at distance 2 from that colored vertex. Now if we use the same coloring scheme for this application, then we need 6 colors. Each different color represents different type of frequencies. For minimizing the number of frequencies, we modify the square coloring scheme, that is a new coloring scheme, Q subset square coloring. In this, the coloring function maps from vertices to C0, C1 to CQ colors, where C0 represents uncolored vertices. In this coloring scheme, we are not coloring entire vertices in that graph. We are coloring only subset of the vertices and uncolored vertices represented by the color C0. If there exists a Q subset square coloring on a graph G, then it should satisfy the following two constraints. For every vertex and every color Ci, where I is from 1 to Q, the closed neighborhood of V intersection colors is less than or equal to 1. And there will be at most degree of V number of colors with color C0 in its closed neighborhood of that V. We can see this in detail. Every vertex has at least one colored vertex in its closed neighborhood, and no color is repeated in the closed neighborhood. The main important property of this Q subset square coloring is the set of colored vertices form a dominating set of the graph. To color a graph using Q subset square coloring in a simple way, a distinct color can be used for every vertices. so that the objective is to minimize the number of vertices. This is called a subset square chromatic number. This is one example. In this graph is colored using square coloring. In that we need 5 colors. The same graph we can color it using 2 colors when we are coloring it using Q subset square coloring. If we solve the same problem that we mentioned earlier, if we use Q subset square coloring, we need only 2 frequencies. And this concept of subset square coloring can also be studied in the context of a classical problem in computational geometry called art gallery problem. Given a polygon P along with the 2 sets M and G of the points in P, and the art gallery problem is to find the subset of G for every point in M is seen by at least one point in G prime. In chromatic art gallery problem, our aim is to find G prime, and G prime can be colored using Q colors, and every point M is seen by at least one point in G prime. Moreover, every point in G prime that since M get distinct color. So that and if M and G are the same finite set, then the chromatic art gallery problem can be reduced to Q subset square coloring of a visibility graph. So that we can use Q subset square coloring problem for the applications in robotics. Another motivation for studying Q subset square coloring is that many graphs tend to use much smaller number of colors for Q subset square coloring when compared to square coloring problem. And the efficient dominating set problem is another problem which is closely related to Q subset square coloring problem. An independent set C of vertices in a graph is an efficient dominating set when each vertex not in C is adjacent to exactly one vertex in C. And this efficient dominating set problem is NP complete. And this is a special case of Q subset square coloring problem. So that Q subset square coloring problem is also NP complete. These are the bounds of subset square chromatic subset square coloring for some basic graph classes. For a path graph, we need only one color to dominate the entire vertices in that path. And for a cycle with the 3n vertices, also we need only one color. But the cycles with a 3n plus 1 or 3n plus 2 vertices, we need chromatic number as 2. For a complete graph, we need only one color. The complete graph, the dominating set is also 1, so that we can color that vertex. In the grid graph, we need 2 colors. The subset square chromatic number of some other graph classes are this bipartite graph. A caterpillar graph is a superclass of bipartite permutation graph. And the bipartite permutation graph needs 3 colors, and the caterpillar graph is also needs 3 colors. And the tree is a superclass of caterpillar graph, and there exists some trees which needs root and colors. And the threshold graph is an intersection graph of a split graph and co-graph. And the threshold graph needs only one color. The co-graph is also needs 2 colors. There exists some split graphs which needs root and colors. The bipartite graph is a superclass of complete bipartite graph, tree, and bipartite permutation graph. And there exists bipartite graphs which needs root and colors. And the chromatic subset square chromatic number of a planar graph with diameter 2 needs 2 colors. And the subset square chromatic number we can bound with respect to some other graph parameter, which is the subset square chromatic number we can bound it using the square of maximum degree and size of vertex cover and size of cluster vertex deletion, neighborhood diversity, modular width. And when it comes to algorithmic question, the question is Can G be Q subset square colored? And we already know that, we already said that efficient dominating set is NP complete. So that Q subset square coloring is also NP complete. Now, these are the NP completeness results which we have. Q subset square coloring problem when Q equal to 2 is NP complete even on planar bipartite graph. And the problem when Q greater than or equal to 3 is NP complete even on bipartite graph. Now we are interested in parameterized complexity. In that we are expecting a running time, which is a function of that parameter and into size of the input. The theory of intractability of a parameterized problem, we can order this problem into the hierarchy that's called W hierarchy. And we can now consider different parameters. The first we can consider a standard parameter, that is number of colors. The efficient dominating set is a special case of subset square coloring problem where the number of color is 1. So that we can prove that Q subset square coloring problem parameterized by number of color is para NP hard. And the problem remains W hard even on the graph with diameter 2. Now we can consider a well-studied structural parameter, that is tree width. Several hard problems are FPT when parameterized by tree width. But in Q subset square coloring problem, parameterized by tree width is W hard. The square coloring problem is W hard parameterized by tree width. We can modify the graph construction that is used in the proof of square coloring problem. Then we can prove that Q subset square coloring parameterized by tree width is also W hard. Now the interesting result is when we are parameterized by tree width plus number of color, then we can show that Q subset square coloring problem is problem parameterized by tree width plus number of colors is FPT. And for this, we are using a standard technique, that is deep dynamic programming over tree width. Now we can consider some parameter which is possibly larger than the size of tree width. One such parameter is size of vertex cover. The number of colors used in Q subset square coloring problem, we can bound it by size of vertex cover. And also tree width we can bound using size of vertex cover. Now the combined parameter tree width plus number of colors, we can bound it by size of vertex cover. And we already shown that tree width plus when we are using parameter tree width plus number of color, it's FPT. So that we can say that Q subset square coloring problem parameterized by size of vertex cover is FPT. Now we can note that the size of vertex cover is possibly larger, usually a larger parameter on dense graphs. So now we can consider the parameter which have a value smaller in dense graph. One such parameter is neighborhood diversity. And for that parameter, the Q subset square coloring problem parameterized by neighborhood diversity is FPT. And the interesting result in that parameter is it admits a polynomial kernel. And now we can consider a parameter which is less than the size of vertex cover, that is distance to cluster. Q subset square coloring parameterized by distance to cluster is FPT. We can look at it in detail later. Now we can consider another parameter, that is twin cover, which lie in between the distance to cluster and size of vertex cover. And we are getting a better running time than compared to distance to cluster. Now we can give a closer look on the parameter distance to cluster. The cluster graph is a disjoint union of complete graph. The subset square chromatic number of a complete graph is 1. So that subset square chromatic number of cluster graph is also 1. The distance to cluster parameter is if we remove a set of vertices x from the graph, then if the remaining graph G of V minus x is a cluster graph, then the cardinality of X is called a distance to cluster. We are considering this as our parameter. So if number of color is greater than k plus 1, then we can color the vertices in X using k colors, and one extra color that we can use for cluster graph. So that subset square color on this graph using k plus 1 more than k plus 1 colors, then there exists a subset square coloring. Now we can assume Q is less than or equal to K. In this proof, we are going to bound the number of vertices in cluster graph using the function of K. If two or more vertices in a clique have a same neighborhood X in X, then we can delete all but one of these vertex. The vertex which dominate this vertex can also dominate the deleted vertex. So that we can say that in every clique, there will be at most 2 power k vertices. Now we need to bound the number of cliques. For that, we can consider a family of subsets of X, that is x1, x2, etc. up to x2 power k. Let's consider two cliques CA and CB. For all I, where I is from 1 to 2 power k, if either both CA and CB each have a vertex whose neighborhood in X is xi, or neither of them has such a vertex, then we can say that these two cliques CA and CB are the same type. Now there will be at most 2 power such distinct type of cliques. Now we don't need to keep all cliques in the same type. If there exist more than q power 2 power k plus 1 cliques of the same type, then we can delete all but 2 power k, q power 2 power k plus 1 of them. Now we bound the number of vertices in cluster graph. It's 2 power k into q power 2 power k plus 1. So there will be at most k plus 2 power k into q power 2 power k plus 1 vertices. Now we bound the number of vertices in this graph by function of k. Now we can say that Q subset square coloring parameterized by distance to cluster is FPT. These are the summary of results in parameterized complexity, and all these parameter we got FPT algorithm, and when the parameter is tree width, its Q subset square coloring problem is W hard, and when we are taking number of colors as a parameter, it's para NP hard. Thank you.